In the previous video, we have talked about the rocSPARSE library, which provides the primitive APIs for linear algebra operations. In this video, we're going to introduce rocSPARSE, which is a similar library, but to work on sparse data. Sparse data is everywhere. So for example, in network data, we can see these connections are not between all the nodes. There are only a few connections, but all the nodes are involved. This type of data widely exists in our big data era. For example, on Facebook, we can see all the users are not all-to-all connected. There are only a few friendship relationships, but there's a big network between users. And this type of data are everywhere. For example, users and YouTube videos, users and products sold on Amazon. Those are all sparse data. So we need to have an efficient way to process this type of sparse data. When dealing with big data, we have to consider the curse of dimensions. For example, if we're a social media website and there are only 16K users on our website, and we can see how many data we need. Only these are small data. If we really need to consider all-to-all connection, we already need to consume 1 GB of data. If we have more users, we may need more data, which is not practical. And in terms of friendship relationship, it's not all-to-all relationship. We don't really need to store all this data. That's why we need to consider sparse data and only consider those connections in this data. When we say sparse data, we consider vectors or matrices with a lot of zeros in it, and only a few pieces of data has non-zero value. So there are many different ways that we can store sparse data, or sparse matrix in particular. For example, we have the coordinate representation, COO, the compressed sparse row representation, BSR, GE, BSR, EAL, HYB. There are countless of sparse matrix compression method, but the COO and the CSR are the most commonly used representations. So in this video, before introducing the rocSPARSE library, let's talk about the COO representation first. Assuming we have this matrix, we can see it's a 5x3 matrix, and there are a few zeros in it, and about half of the fields has value and half of the fields are zeros. So how we can compress this data without really storing this 15 pieces of data? In general, sparse matrix needs to store the matrix in a few vectors with different semantics of the data. In COO representation, we first want to have an array that stores all the non-zero data. For example, here we store 1.0, 2.0, all the way to 8.0. And then we need to store the coordinates of each value. So we need to have two more vectors. One is the COO row index, one is the COO call index. So let's look at the first element in all three vectors. This value is 1.0, and the row coordinate is 0, and the column coordinate is 0. So look at 5.0 again, and the row index is 1, and the column index is 2. Basically, with these three vectors, we can store all the data that is originally in the sparse matrix. We also need a few extra fields, that is m equals 3, that's the number of rows, and n equals 5, that's the number of columns, and nnz is a number of non-zero element. nnz, which is 8. There are 8 non-zero elements. Those are some metadata that you need to store for this matrix. So we need to consider the advantages and disadvantages. The advantage of this method is it's really simple. That we can spend 2 minutes to introduce this format. That is a good sign this is simple. But the disadvantage is that it requires 3 times of nnz storage space. We need 3 vectors, and all the 3 vectors should have the same length. And also, if we want to access a particular location, say if I want to add row 2, column 3, basically we need to traverse from the beginning. We need to go through all these non-zero elements until we reach that point. So is there a way that we can reduce the storage space? And if I want to access a particular location, is there a better way that I can access that point? Basically, with COO, we cannot do it, but we can use another method called CSR method, compress sparse row. Let's consider the same matrix. We still need to store all these values, and this time we store in CSR value vector. So we mark all the indices in this vector. Next, we can consider these a few special values. Those are the first values that belongs to each row. For example, 1.0 is the start of the 0th row. 4.0 is the first element in the first row. And 6.0 is the start of the 2nd row. So can we store this type of data? Let's store this data there. Let's name it as CSR row pointer. So we know that if we want to access the first row or the 0th row starts from index 0 in the CSR value. If we want to directly access the 2th row, I don't want to say second because it's a 0-based index. So if we want to access the element in the 2th row, we can directly access the 5th element. We know it starts from the 5th element from this row pointer vector. And then we also need to have one extra element. This will be very helpful that it can store the last element. Then we need to store one extra field. We store the length of the CSR value array, and we put it at the end of the CSR row pointer. We know there are 3 rows, so we won't use the last one when we access fields. And then similar to COO method, we can have this CSR call index, which basically stores the column index of each element. So the length of this vector must equals to NNZ. We also store M, N, and NNZ, which is the same as the COO format. So what's the advantage of CSR matrix? So first of all, we don't really need 3 times of NNZ. It saves some space. It's basically 2 NNZ plus M plus 1. Since M is likely to be smaller than NNZ, we think CSR will save space. But that is not the most important advantage. The most important advantage is that we can access a particular element by its index. So if we want to access an element at the 2th row and the 3rd element, what we can do is we can directly go to the 2nd element or the 2th element in the row pointer. We find it's 5. Then we can directly go to the 5th element, which is 6.0 in the CSR value. Then we traverse not the whole matrix, but only that row. We go to 6.0, we see, okay, it has the column index of 0. Then we can check 7.0. We know that this element has column index of 3. Then we find a good location. So in COO, every time we want to access a point, we need to traverse the whole matrix. But in CSR, every time we want to access one element by the coordination, we only need to traverse the row, which is much more convenient compared to COO format. It's very important to understand this format, and only after understanding this format, we can try to understand a rocSPARSE example and see how the API is used. Let's start with this example of multiplying a CSR matrix with a dense matrix. So at the beginning, it's very similar to rocBLAST library. We include HIP runtime and the rocSPARSE header file. We also need cstdlib and vector libraries. In the main function, we assume density is 0.9 and the size is 8K. So we want to keep consistent with the previous example in the rocBLAST video. We have 3 matrices, HA, HB, and HC. Next, we randomly generate the data. We generate the data in the format of dense matrix. Then we convert it into a CSR format. If you are interested in how this conversion is done, you can pause the video and read this part of code. But I think if you understand the CSR format, you don't really need to spend too much time understanding this piece of code. You just need to understand that after this code is executed, we have this hRow pointer, hval, and hcall index. These 3 vectors are properly set to represent the matrix in CSR format. Next, we allocate some memory, and we copy the memory from the host to the device side. Next is the main part of this program. Similar to rocBLAST library, we need to create a handle. This handle stores contextual information like which device we want to use, which stream we want to use. We need to define 2 scalars, alpha and beta, and we need to define a matrix descriptor. For now, we can use the default field for this matrix descriptor, but when we are dealing with more complex data structure, you may want to modify some field of this matrix descriptor. I'm not going to introduce this matrix descriptor in detail. If you are interested in using it, or you want to use some non-standard format, you can refer to the rocSPARSE library documentation. And next, also very similar to the rocSPARSE example, we call the main function. And this time, this function is named as rocSPARSE SCSRMM. The first S here stands for single precision, CSR stands for the format, and MM is matrix-matrix multiplication. You can see there are a ton of arguments in this function. I will leave it to the audience to check what these arguments mean, what's the order. And finally, we check the status. We want to make sure this program runs properly. And at the end, we free up all the memories that we have allocated. We use rocSPARSE because we expect it can deliver higher performance for sparse matrices. For most of the time, you probably cannot really make a decision if you want to use rocBLAS or rocSPARSE. This is because your program has already been written that your input data or your output data is already defined that it should be in sparse format or dense format. For most of the time, converting from dense format to sparse format or converting back from sparse format to dense format is actually quite slow, so it doesn't really worth the effort of converting the format. But if you're designing some algorithms from scratch, you probably can make a decision if you want to use dense matrix or sparse matrix. So in this particular experiment, we want to make a comparison. We want to compare the performance of the rocBLAS library and the rocSPARSE library. And in this example, we're still using the 8K by 8K by 8K example, so the data size is the same. For the dense matrix, the performance is deterministic. No matter if you have 0 or non-zeros, MI50 and MI100 will deliver the same performance regardless of the density. But the rocSPARSE library will deliver a different performance. And this density is in log scale. So for example, 10 to the power of minus 2 is 1% of density. That means 1% of element is not 0. So as you can see from this figure, if the density is below about 2%, we should use rocSPARSE for M150 GPU. And if the density is below 1%, we should use rocSPARSE on M100 GPU. M100 is actually very efficient for rocBLAS implementation, but for rocSPARSE, we probably cannot really utilize the matrix unit. That's why this cutoff point is lower for MI100. And I have to say, in this example, one of the matrix is transposed, which is in favor of the rocBLAS library and is not in favor of the rocSPARSE library. If you want to implement an algorithm, don't fully trust this figure, but you should do the experiment on your own. And finally, what APIs rocSPARSE provide is actually very similar to rocBLAS, and we have level 1, level 2, and level 3 operations. In level 1, we're dealing with vector. In level 2, we're dealing with matrix and vector operations. rocSPARSE has more APIs because it needs to deal with different formats, but it also has fewer formats because it only processes this general matrix vector multiplication. We do not have those triangle or symmetrical matrix vector multiplication. And finally, for level 3 APIs, we have this MM, matrix operations. As you can see here, we have BSR, CSR, we have different type of format. And also here I'm only listing the single precision APIs. rocSPARSE also support the double precision and half precision.